Good evening, students. Welcome to HashLearn. I'm Srihash, your physics mentor. We are dealing with a chapter called as wave optics, and we are in the end of the chapter. So the last concept which we have to know is called as the polarization, and we will be solving the numericals in the next class, the multi-concept problems as usual, our routine. So we are dealing with the chapter called as wave optics, and we are at the end of the chapter, which is the last topic of the chapter, which is called as polarization. So the recap of the previous class, we studied diffraction and the numerical problems based on that. If I have to summarize the entire diffraction in one single line, it is called as the special case of interference. It is called as the special case of interference. So whatever was the condition for the maxima in interference is now the condition for minima in the diffraction, or whatever is the condition for minima in interference is the condition for diffraction maxima. Hello Yogesh, very good evening, welcome on board, welcome to HashLearn. So this was the diffraction, which is read as a special case of interference. So whatever happens at the interference will be acting reversal in diffraction. So I hope you are clear with that. So the diffraction and the difference is when you plot the interference fringe. Hello Akshay, very good evening. The intensity versus distance curve in the interference. Each band has the same intensity and same width. Whereas in the diffraction you will have it as the central bright maxima followed by minimas. Central bright maximas and the minimas. So this was the diffraction and the interference pattern. So now we have, we'll go to the next concept, which is so before we have the most important CPP question from the last class. In YDSE, Young's double slit experiment, the source of light of wavelength 6320 Armstrong, the first maxima will occur when the phase difference is. For maxima, we know the condition is delta x is equal to n lambda, so delta is equal to lambda. So the phase difference is 6320 Armstrong. So that was the condition. Now we are going into the polarization and the numerical problems on that. So basically, what is polarization? And I'm pretty sure this word is not new to us. We have dealt this polarization, the concept or a similar concept which is called as polarization in electrostatics. So let us say you take a dielectric medium. The dielectrics are made up of two types. One is called as polar and the other one is called as non-polar. So when you have a polar molecule, the centers of the positive and the negative will not coincide, whereas in non-polar, the centers of the positive and the negative charges coincide. So if you take any kind of dielectrics, when you apply an electric field, they start moving towards one condition. If the electric field is increased, then you will have plus on one side and minus. You will have all the negative charges and all the positive charges on the other side. So here what is happening? We are acquiring a state called as one-sidedness, which means all the negative charges are moved to the left hand side, all the negative charges are moved to the right hand side, or all the one type of charges are moved to the one hand side and all the other type of charges are moved to the other side. So the phenomenon of obtaining one-sidedness is called as the polarization. Now how is that related to optics? We'll see into that. The first one to know about this is, so the person called as the Maxwell, he was a person who proved that light is an electromagnetic wave. So when you have an electromagnetic wave, let us say this is the propagation of light. I'll call it as c, the speed with which it is moving. So these are the electric field vectors. According to the Maxwell, light is an electromagnetic wave. According to Maxwell, the light is an electromagnetic wave. So this is in the direction in which the electric fields are vibrating. The electric fields are vibrating in this condition. So perpendicular to this will be the So perpendicular to this will be the magnetic field which is vibrating in the condition. So this is the magnetic field which is vibrating perpendicular to the magnetic field. So when you have a electromagnetic wave, you have the electric field and the magnetic field vibrating perpendicularly to each other, something like this. So you can take like this. So this is the direction of the electric field and the magnetic field. If the electric field is vibrating like this, then the magnetic field will be vibrating like this. So there are certain type of materials which are called as the polarizers. What do they do is the main concern over here. So let us assume you have an electromagnetic wave. So this is the electric field and the magnetic field. So now what I will assume is, if this is the direction of the light which is propagating, I'll assume these are the electric field vectors and perpendicular that will be the vector. So it will be covering 360 degrees. So if I draw a front view of the diagram, so this will look like this. So this is the field vectors which are vibrating. So it is vibrating in all the directions. I'll be confining it to the only one particular direction, that is along the x-axis and the y-axis. If I allow this electric field vectors or the EM waves to pass through a polarizer, so I'll pass it through a polarizer. So now what happens over here is you will have only one directional electric fields and the perpendicular ones will get cancelled out. So now you can imagine it something like this. So you have a slit or an opening like this, and in this you have the directions like this. So you have the directions like this. Let us take the directions are something like this. Now these red pens represents the electric field and the magnetic field which are perpendicular to each other. When I allow it to pass through a slit something like this, so now what is happening? The perpendicular plane is getting blocked, whereas this is allowed to propagate. So what happens when the light comes after the polarizers, comes from the polarizer, you will have only these field vectors vibrating. This will be blocked. So this will be blocked. So which means this is the blocked electric field vectors and this will be allowed. So that is called as the plane of polarization. So that is called as the plane of polarization, and which is allowed. So now due to this, what will happen over here is, if you remember your waves which you have studied in your class 11, we know that intensity is proportional to amplitude square. So now you have, this is the ray of light, you will have only this which is allowed and the perpendicular ones are blocked. So this intensity gets reduced by 2. So where I naught is the initial intensity, after passing through the polarizer, it gets blocked. So this is called as the plane of polarization, and this is called as the plane of transmission. Wherever the electric fields are present, that is called as plane of transmission, and whichever has got blocked, that is called as the plane of polarization. So this is something which you have to know. So let us assume another situation over here. So you have an unpolarized light. So this is the direction of light, where the light waves are traveling like this. This is the electric field vectors, and this is the magnetic field vectors or the electric field vectors. You allow it to pass through one polarizer. So you will have only the vectors perpendicular to the light field. If I have one more polarizer kept at a certain angle, so if you take this is the angle between them is equal to theta. The angle between them is equal to theta. So now what happens over here is the intensity obtained after the double polarization or through any polarization, I is equal to I naught cos square theta is the formula which you have to remember. So I is equal to I naught cos square theta, where I naught is the intensity of unpolarized light. So I is equal to I naught cos square theta, where I naught is intensity of unpolarized light. intensity of unpolarized light, and theta is the angle. And this is remembered as Malu's law. So this is remembered as Malu's law. The intensity of the polarized light is dependent on the initial intensity and the angle between the polarizer and the transmission axis. So this is very, very important for our problem solving. So this is very, 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 very important. The next thing what we are doing over here is, in how many ways can I obtain a polarized light? We have to know that. The first one is called as polarization by scattering. So polarization by scattering. Now what happens over here is, so now you have an unpolarized light. So one is vibrating in this direction and the other one is vibrating perpendicular to this, and this is called as unpolarized light. And let us assume you have a air molecule present in its path. So when you have an air molecule present in its path, so now what happens is there is an obstacle, the light turns to change its path. So in that, what happens over here is, if the observer is over here, he will receive only one part of light and whose intensity is very much less than the unpolarized light, and this is the polarized light because the intensity is already been reduced. So this light of suitable wavelength will reach the observer and the other gets scattered away from the observer. So this is called as the polarization by scattering. So you can assume it like this. So there is an unpolarized light and the planes are vibrating perpendicular to this. If, let us say, the air molecule, which is when it is incident, it also starts vibrating. So this will wave off these particles and the only horizontal ones are present, are reaching to you. So it is something like you have a which is coming up and down and you also go up and down. So you won't allow that. But the ones which are horizontal will be passed through this. So this is called as the polarization by scattering. Now the most important one is called as the polarization by reflection. So let us assume you have a light which is incident on a surface, reflecting surface, and this is my normal. So you have a ray of light which is incident, and this is supposed to be unpolarized, which is perpendicular to each other. Now we know that a part of light gets reflected back and other part gets refracted. So now what is happening over here is, you have one perpendicular vibration in another and another is in the another plane. So now Akshay, which part I'll come back to it later in the problems. Akshay, I hope you can understand this. So it is something like this. Let us say the particles are the electric field vector is like this and the another electric field vector is like this. If you have an air molecule which is oscillating like this, so what happens when this is oscillating? This will block this vibrations, but these blockings will not disturb this molecule, so only this will be allowed to pass through it. So now what has happened? Now the light has been polarized because the air molecules have blocked these electric field vectors. So I hope it is clear to you now, Akshay. So that was the reflected light. So coming back to this, you have the refracted light and the reflected light. So their intensity is obviously reduced because we have discussed this in the ray optics chapter. So now if I draw a ray diagram to understand this, so let us say this is your unpolarized light. So this is the polarizing and this is the perpendicular ones. So now what will happen? The reflected light will have one certain kind of this one, and this is the refracted ray, which will have the other particles vibrating perpendicular to this. I am very happy that actually your doubt has been clarified. So this is the rays which are emitted. Now if this angle is theta and this angle is also theta because of the law of reflection, the angle of incidence is equal to the angle of reflection. So this is from the law of reflection, that is angle of incidence is equal to angle of reflection. So there exists a particular angle of incidence called as a polarizing angle. There exists an angle of incidence called as the polarizing angle, which is represented as theta p. So polarizing angle is that angle of incidence. So it is that angle of incidence for which the reflected ray is completely polarized. The reflected ray is completely polarized. The angle of incidence for which the reflected ray is completely polarized is called as the polarizing angle. And for that theta p, the angle between the reflected ray and the refracted ray is equal to 90 degrees. So you have to remember this: when the angle of incidence is exactly equal to polarizing angle, the reflected ray is completely polarized, and the angle between the reflected ray and the refracted ray is always equal to 90 degrees. Now using this, let us assume you have a medium of refractive index n, and this is the normal, this is the unpolarized light, and the reflected ray is completely polarized. The reflected ray is completely polarized, and the angle between the reflected ray and the refracted ray is equal to 90 degrees. So from this you will have, if this is polarized, even this will be polarized. So now we have that from the Snell's law, you have that n is equal to sine I by sine r. But from here the condition is so here I is equal to theta p. So from this you can write it as n is equal to sine theta p divided by sine r. Now we know that this is a straight line, so the complete angle is 180 degrees. So angle of reflection, so if this is theta p, even this will be theta p, and this is angle of reflection r, plus 90 plus r is equal to 180 degrees. So from this you will have it as theta p plus r is equal to 90 degrees, or r is equal to 90 minus theta p. On substituting that value, you will have it as n is equal to sine theta p divided by sine of 90 minus theta p. We know that sine of 90 minus theta is equal to cos theta p, which implies n is equal to tan theta p. So the relation between the refractive index and the polarizing angle is polarizing angle is equal to n is equal to tan theta p, or the refractive index is equal to the tan of the polarizing angle, and this is called as Brewster's law. So this is called as Brewster's law. So this is very, very important for us to solve the problems. So I hope you have understood the concept, students. So now we have the first problem on the screen. A ray of unpolarized light is incident on a glass plate at the polarizing angle. So what is the first thing? What will happen? the reflected ray and the transmitted rays are completely plane polarized. The reflected rays is completely polarized and the transmitted ray is partially polarized. The reflected rays is partially polarized and the transmitted ray is completely polarized. Or what is the correct option? Okay, so Yogesh says 1B. What about others? So this is from the Brewster's law, student. So 1B is correct. Correct. Good job, Yogesh. So remember this: when the ray of light is incident at the polarizing angle, the reflected ray is completely polarized. And this is inside the medium. So obviously due to the refractive index, the polarization may be little less, ideally speaking. So the correct answer is 1B. Good job, Yogesh, and good job, Peru. So now we have the next problem on the screen. A parallel beam of incident light is incident at an angle of 60 degrees on a glass plate surface and the reflected beam is completely polarized. What is the angle of refraction? Also calculate the refractive index of glass. A parallel beam of light is incident at an angle of 60 degrees on a glass plate surface and the reflected beam is completely polarized. What is the angle of refraction? What is the angle of refraction? Also calculate the refractive index of the glass. So here theta is given. So you will have it as n is equal to tan 60 degrees from the formula n is equal to tan theta. So from this you will have it as n is equal to tan 60, so which is equal to 1.732, which is as simple as writing it as root 3. So from this you will have it as n is equal to sine I by sine r. So from this you will have it as n is equal to, sine r is equal to sine I by root 3. So sine r is equal to root 3 by 2 into root 3, which gets cancelled. So r is equal to 30 degrees. So now you will have it as, so what is the first one? Angle of refraction is 30 degrees and the refractive index of glass is root 3. Good job, Peru. So you have given the answer. So I think you have taken little more time, greater than 1 minute, but very good try. Very happy. So this is the second problem. Now we have the third problem on the screen. For a given medium, the polarizing angle is 60 degrees. What will be the critical angle? What will be the critical angle for this medium? So I think you remember what is critical angle, which we have done in the chapter ray optics. So from this you will have theta equals 60 degrees. So from this n is equal to tan 60 from the polarizing, that is n is equal to tan theta. So you will have it as n is equal to root 3 and we know that n is equal to 1 by sine c. So what is critical angle? Let us say this is your denser medium and this is your rarer medium. So if this is the normal, you have a ray of light which is incident at an angle of critical angle, then the angle of refraction is equal to 90 degrees in the rarer medium. So critical angle is that angle of incidence in the denser medium for which the angle of refraction in the rarer medium is equal to 90 degrees. So the angle of incidence in the denser medium is called as critical angle for which the angle of refraction in the rarer medium is 90 degrees, and n is equal to 1 by sine c, or sine c is equal to 1 by root 3, or sine c is equal to 1 by 1.73, which implies sine c is equal to 0.57 and c is approximately 35 degrees. So good job Peru. Sine c equals 1 by root 3 is the correct answer. So this is very, very important. So now you can see how we have chosen a problem which is involving ray optics into it. The next problem is on the screen. Two cross polarites are placed in the path of a light. In between these, a third polarizer is placed, whose makes an angle theta with the polarization of the first polarite. Determine the intensity of the emerging from the third polarite in terms of theta. Assume that the intensity of light emerging from the first polarite is I naught. So let us draw the diagram first. I hope you will have a clear picture on that. So now this is my reference axis. The first polarite is something like this. The second polarite is exactly something like this. So which means if the first polarite is like this, the second polarite is 90 degrees. In between these two, there is one more polarite which is making an angle of theta. So let us say this is something like this. So which means if I draw the structure, so this is the first line, second line and the third line. The first line, sorry, I'll take three different colors. So for the first line, this is the first polarite, it is something like this. And the second polarite is making an angle theta. So this is the axis of the polarite which is making an angle theta. And the third polarite is perpendicular to the first one. So these two angle is 90 degrees and this will be 90 minus theta. So I hope you have a clear picture now, students. So now from this, so you have the first light coming out. The light comes from the first polarite S. So where I naught is the intensity of light from the first polarite, and from the second polarite it will be equal to I equals I naught cos square 90 minus theta, which is equal to I naught sine square theta. So from the second, sorry. So from the first polarite, so from the second polarite, it is equal to I naught cos square theta. So this is from the second polarite, and from the third polarite, it will be equal to, this is I naught. So I naught cos square 90 minus theta, which is equal to I naught sine square theta. So if you have to, since the light of intensity is equal to from the third polarite, so you'll have it as I is equal to I naught cos square theta sine square theta. So from this you will have it as I naught sine 2 theta by 2 the whole square. This is your basic trigonometry, students. So from this you will have it as I naught by 4 sine square 2 theta is the intensity emerging out from the third polarite. So this is the intensity of light emerging from the third polaroid, or you can also put it as I naught square sine square theta is also the answer. So but we have to write I naught will be this is equal to, in terms of the second one. So this will be I times, and I is equal to I naught cos square theta. You substitute that value, because for the third polaroid, the incident light will be the light coming from the second polaroid. So I hope you have cleared this, students. The next problem is on the screen. A beam of plane polarized light falls normally on a polarizer of the cross-sectional area 3 into 10 power 4, which rotates about the axis with an angular velocity of 31.4. Find the energy of light passing through the polarizer per revolution and the intensity of the emergent beam if the flux of energy of incident beam is 10 power minus 3. Very nice problem. So now the given data over here is area equals 3 into 10 power minus 4 and omega equals 31.4 and flux equals 10 power minus 3. So I naught will be flux upon area. So I naught is 10 by 3 watt per meter square. Now the energy transmitted I is equal to I naught by 2, which is equal to half into 10 by 3, which is equal to 5 by 3. So the energy transmitted is 5 by 3, which is equal to 1.67. So after the polarization, you'll have it as I equals I naught square cos square theta. So which is equal to 5 by 3 into cos square theta. So which is equal to 5 by 3 into half. Because when it rotates with an angle of omega is 31 pi by 4. Hi Arun Prasad, welcome to HashLearn. Welcome on board. You are no worries, you are new to the HashLearn or old to the HashLearn, but according to me you are old to physics, so that is sufficient for us to get connected. So cos square is half because it is taking 31 by 4. So if you take the circumference of the circle and calculate the time taken, so that will be equal to cos square theta is equal to 60 degrees, so which is equal to half. So from this the energy transmitted is I into A into T. So which is equal to I average is we have calculated as around 5 by 6 into area is 3 into 10 power minus 4 and the time period is 2 pi by omega. So from this, if you will have the answer as 10 power minus 4 joules is the energy transmitted, and this 1.67 watt per meter is the intensity. So this is the problem. Now before we continue with the problems, we have the previous class contest question for you. So if the frequency of a wave is 360 per second, the distance between nearest to two compression and rarefaction is 1 meter. Find out the velocity of the wave. So you just have to v equals f lambda. So you have to find out the velocity. So the distance is given as 1 meter. You have to go back to cyclotron is explained in moving charges and magnetism approximately in the month of June or July, Arun. So you can go back to that. So very sadly we have no winner this time. So now we have the today's contest question. So students, remember that the options are W, X, Y, Z and you have no multiple entries, please. So right students, the winner of the contest question will be announced in the next class. So now we have the next problem. A beam of light is passed through a polarizer and an analyzer. The latter is set for the maximum intensity due to transmission, and to reduce the intensity to I 1/4 of the fraction, one tries the four ways of turning the analyzer and the polarizer. So the first option is analyzer by plus 20 degrees and the polarizer by minus 40 degrees. And the second option is analyzer by plus 75 degrees and polarizer by plus 15 degrees. Third option, analyzer by minus 60 degrees and and polarizer by 0 degrees. And the fourth option is analyzer by 0 degrees and polarizer by minus 60 degrees. So remember students, over here plus stands for clockwise and minus stands for anti-clockwise. So in what way should I rotate the analyzer and the polarizer such that the intensity reduces to 1/4? So first thing over here is, you will assume this is the propagation of light and this is the polarizer. When you rotate it by 20 degrees, it is reduced to 60 degrees. So in first case, theta equals 60 degrees. So I is equal to I naught cos square 60, which is equal to I naught by 4. So the first case is possible. The first case is possible. In the second case, theta equals 75 minus 50, which is equal to 60, which goes back to the same case. So even second case is also possible. And in third case, the theta is directly given as 60 degrees. So which is equal to, again goes back to the first case. Even this is possible. In fourth case, again theta is equal to 60 degrees. So it will come back to first case. So in all the four cases, it is possible. In all the four cases, it is possible to get the intensity as 1/4 of the original intensity. The next problem is on the screen. Right, so this was the continuation of the previous slide. So the answer is all four. So now we have the numerical problem 8. Two nickel prisms are placed with their principal planes at an angle of 60 degrees. What percentage of light incident on it combination is transmitted? So the angle is 60 degrees. What is the percentage of light which is incident on the combination is transmitted? So in the first case, so you have the unpolarized light and you have a prism and you have another prism such that the angle between them is 60 degrees. So here it is I, it will become I naught by 2. Here it is I naught by 2 cos square theta. So if you take that into consideration, you'll have it as I is equal to I naught by 2 into cos square 60, which is equal to I naught by 2 into 1/4, which is equal to I naught by 8. So the answer is 12.5%. So I think Yogesh shouldn't consider the first prism, which is giving rise to half intensity, and that is allowed to pass through the another prism. So I hope that is clear to you. So now we have the next problem on the screen. Two linear polarizers are crossed at an angle of 60 degrees. The fraction of intensity transmitted by the pair is 1/4, 1/8, 3/8 and half. Which is the correct answer? I think you don't need 60 seconds to solve this. You can solve it in a lesser time. This is same as the previous problem. There it was asked in percentage, now it is asked in fraction, so the answer is 1 by 8. So this is same like your problem 8. Sorry, this is same like your problem 8. This is same problem where it was asked in percentage, now it is asked in fraction, so the answer is B. Good job, Yogesh. So the next one is, this is very, very simple. What is the angle between the direction of oscillation of light waves and the direction of propagation? So it is as simple as asking what is the direction between the electric field and the light propagation. So this is very simple, students. The answer is pi by 2. I had told you, remember this. So if the light is traveling in one direction, electric field is propagating perpendicular. The magnetic field is also propagating perpendicular. So the answer is pi by 2. So now I have one problem, two problems for the homework for you. So this is the one problem which is homework. And now you have the another problem. So the statements are given. You have to find out the relation between them. So is the correct answer, what is the statement 1 and what is the statement 2? Yes or no, you have to prove it. So now that was the for today's class, students. So we have dealt with the polarization, and in the next class we'll be continuing the numericals. And thank you, students, for joining us. I hope you like this class. If you like them, please do share this video among all your friends and help them. Now it is CPP time. It is available for the passport members. We have chosen 10 best questions on the topic, and it is unlocked and available for passport members. And non-passport members, you have to subscribe to passport. Once you subscribe to passport, you won't get only the questions, but you'll also be getting access to 24/7 one-on-one doubt solving, plus practice and test questions from the best-selling books, and all the video classes covering the concepts whatever you need. And passport members, please start solving the CPP questions right away. All the very best. See you in the next class. Till then, keep smiling, keep solving. Good night. Sayonara.